So what we've seen so far is that we have our two energy levels within this atom, this molecule, ion, whatever it is, inside the laser material, and we can have transitions going from level 1 up to level 2 through absorption, and going down from level 2 into level 1 through spontaneous emission, so a random process, and stimulated emission, which is the one that will generate the laser light, and that's the one that we want to maximize. And we've also seen that the energy levels are not infinitely well defined. They're not infinitely sharp. They have some range of values, a distribution of values, and that the light which is absorbed or stimulated emitted, will also have a range of different frequencies involved in it as well. Okay. So we have our two-level system. We have absorption, we have spontaneous emission, and we have stimulated emission. And the condition that we said was that for that simple two-level system, it was that the energy, the frequency of the incoming photon had to match the energy gap between those two. But now that we have a range of frequency, a range of values for energy level 2 and a range of values for energy level 1, then we can have a range of different frequencies which can interact with that. So either thinking of emission or absorption, then we will have some distribution of frequencies with a centre frequency at nu naught, and that's our line shape function. And we saw that the value for a line shape function depends on what's happening inside the laser, whether we have homogeneous or inhomogeneously broadening, and whether we have Lorentzian or Gaussian distributions. So let's think now about the processes that we actually want to maximize and the ones that we want to minimize within the laser. Well, what we would like is we'd just like stimulated emission coming out of the laser, the box of the laser on its own, and we would like to have not much absorption going from level 1 up into level 2, because anything that's being absorbed is being lost, and we're not getting that stimulated emission that we want. And we also don't want to have as much a spontaneous emission. Now, with a two-level laser, the only way of getting into level 2 is from level 1, so you have to have that absorption. So let's go back to the equation that we had before for our nice, simple, infinitely sharp two-level system. And we saw that the rate of change of the number of atoms in level 1 or level 2 depended on the absorption, the stimulated emission, and the spontaneous emission. We're going to assume that the spontaneous emission is practically zero, that we can ignore that because that's just a noise term. So if the laser is working well, then the amount of spontaneous emission will be very, very small. Okay. We also made some assumptions about the degeneracy, and we said B12 equals B21, and that means that we can rearrange this equation to get this answer here, which you'll see that the rate of change of the number of atoms in level 1 depends on the difference between the number of atoms in level 1 and level 2, and also depends on the number of photons coming in. Now that relationship is assuming that we have an infinitely sharp transition. In other words, the line width for that transition is 0, so it's not broadened, and that the input signal, the thing which is being absorbed, the signal which is being absorbed, or the signal which is creating the stimulated emission, it also has an infinitely narrow line width. So let's think about what we've seen already with the broadening. We looked at what happens if we consider an interval delta nu, and that delta nu is the full width, half maximum for the distribution, for the Lorentzian or the Gaussian, and d nu is the line width of the input signal, or the signal which is creating the absorption or creating the stimulated emission. And it has some sort of centre frequency at nu naught. So let's have a look at this. So what we've got is the material, the laser material itself is doing something like this. So again, that could be, say, a Lorentzian or a Gaussian, depending on the type of broadening that we've got. And it has a line shape given by G. It has a line width given by delta nu. And what we've got is we've got an input signal. A signal here is being applied at this particular frequency, nu s, and it has its own distribution and its own line width. So how do those two curves convolute with each other? How do they interact with each other? That's what we want to know. So we'll only think about the case where the value, the line width of the signal is very, very much smaller than the line width of the transition. We'll only think about those. We'll use that as one of our constraints or assumptions. So the width of the signal is much, much narrower than the line width of the transmission. Now, in the equation that we have here in 26, we've got the rate of change of the number of atoms in level 1 depends on n1 minus n2. But the number of atoms that can actually interact with this signal is not just n1 minus n2. The number of atoms that can actually interact with the signal is n1 minus n2 times the line shape of the signal times its line width. So essentially it's the area under that rectangle. So that rectangle, the area of that rectangle is essentially what we're looking at. That's a measure of how many atoms can actually interact with that signal. Okay, if we integrate it over d nu, then we get the area under the curve, obviously. So the G function, the line shape function here, times d nu is the probability that a given transition will give you an absorption or an emission in the interval between h nu and h nu plus d nu. Okay, so what are the chances that something is going to happen in this range here? What's the probability? The probability per unit frequency, remember these things all depend on nu, they all depend on frequency, and the probability per unit frequency is then given by the energy, the radiation density times the Einstein coefficient. So the equation that we had above, instead of just having n1 minus n2, we now have to multiply it by the line shape function here of the signal, because only that number of atoms will be able to actually interact with our signal. We'll define our number density, small n, as the number of atoms, or the population of level 1 or level 2, divided by the volume. Now just be careful that this n is not equal to the refractive index. Okay, so we use the same symbol, but just be careful, this is not refractive index, this is the number density. So it's the number of atoms per cubic meter, or the number of ions per cubic inch, or whatever units you're using. So V is the volume and h times nu is the energy for each photon. Then if we multiply by h nu over V, then what we get is the energy for one photon per unit volume. So we multiply all that out, and that then gives us n times h nu. So that's the energy for each photon. That's the number of atoms that can interact with that photon. And so that n times h nu becomes the density, the energy density of the signal field. So it's the number of atoms times the energy per transition with that atom divided by the volume. Okay, so we've got a dB/dt of the expression in the square brackets here, which is equal to rho of nu s, and we can rearrange that then as a nice simple differential equation that the dB/dt of this thing in square brackets is equal to the thing that's in the square brackets times another series of symbols. So that's just like minus dy by dt is equal to k times y. It's that kind of a shape. So what would we expect with that? We would expect an exponential solution for that. So that gives you the rate at which the energy is absorbed by that particular laser material, or the rate at which the atoms are emitting in that laser material. So this is either going from 1 to 2 to 2 to 1. And this is dependent on the difference between the numbers of atoms per unit volume in level 1 and the number of atoms per unit volume in level 2. Okay, so let's look at an example just to make sure that this the assumptions that we've made are kind of reasonable. For a working laser, then the value of the signal line width is very, very much smaller than, or usually generally much smaller than, the transition line width. So if delta nu is 5 angstroms, d nu might be 0.1 to 0.01 angstroms, and 1, for those who have not seen this unit before, 1 angstrom equals 0.1 nanometers. Okay. So that assumption is fairly valid. If we then assume that the value for delta nu is vanishingly small, then we can simplify the equation even further, so that we have minus dB/dt of rho is equal to rho times all of this stuff over here. Now, all of this stuff over here, we want to try and simplify that in some way. We want to try and see if we can gather terms together that make sense for them to be together. Okay. So here, the speed of light is given by c. C naught is the speed of light in vacuum, and now we're going to confuse things even more because we've got this, the refractive index being given by n again, and I apologise for the confusion in this. What we're also going to do is we're going to change the value for the variable, from dB/dt to dB/dx, because what we're interested in is if we've got a box of laser material here, some sort of slab of laser material, what we're interested in is as the light travels through this material, does the intensity grow exponentially or does it decay exponentially? In other words, do we have gain or do we have absorption? That's what we really want to do. We want to find out how does it change as it passes through the material. We're not really interested in how it changes as a function of time. We're interested in how it functions as changes as a function of position within the laser. So remember that for our light rate, our dx by dt is equal to c naught over n. So we can change the variable from dt to dx and integrate that so that we end up with an initial condition, initial signal intensity here of rho naught, and our transition, our energy density as it transmits through the material, rho of nu s, is equal to a negative exponential, as we said, which depends on h times nu, the energy of each individual photon, depends on the line shape, depends on Einstein coefficients, and it depends on the difference between the number of atoms in level 1 and the number of atoms in level 2 per unit volume. Okay, so as I say, what we're going to do is we're going to gather together terms here that make some sort of sense. So we will define the absorption or the gain coefficient, depending on whether we have attenuation or amplification, as being the difference between the number densities times sigma. And this sigma is like a cross-sectional area. It's the effective area for the effective target area, cross-sectional target area for the atom. And if you remember, what I said right at the very start was that if the photon passes close by this atom, then you can get stimulated emission. And I said we would come back to what do we mean by close by. Well, if it falls within that cross-sectional area, then you have a high probability of that interaction happening. So the cross-sectional area isn't the physical cross-sectional area, it's like a kind of effective cross-sectional area or a catchment area for that particular atom or molecule or ion. And the area, stimulated emission cross-section, as it's called, or the absorption cross-section, is given by all these extra bits that are in equation 33. So we've got h nu, we've got b, we've got c, and we've got our line shape function. Okay. So remember that the line shape function, the peak value was inversely proportional to line width. So if we want to have the peak value, if we have nu s equals nu naught, then the wider the transition, then the lower the effective cross-sectional area, and that means that the smaller the absorption or the gain that we get. So going from level 2 to level 1, that's referred to, sigma is referred to as the stimulated emission cross-section. We can then rewrite the equation above to give you a nice simple exponential as the energy density as it travels through the material depends on the initial energy density times e to the minus alpha times x. And alpha is the absorption or the stimulated emission, the gain per unit length. Okay. So let's look at that equation. If so we have that alpha is equal to n1 minus n2 times sigma. If alpha is positive, then this parameter here is an area, so that's always going to be positive. You can't have minus 5 square meters or something like that. It doesn't make sense. So if it's positive, it's because n1 is bigger than n2. Okay, so if n1 is bigger than n2, alpha will be positive. What does that mean? It means that we have this negative alpha times x. So if we start off with rho naught, then if n1 is bigger than n2, in other words, if we've got more atoms in level 1 than in level 2, we're going to get absorption, lots of absorption, and we'll get a negative exponential. Let's look at it the other way around. Let's supposing that alpha was negative, okay? Because then we've got negative alpha, or alpha is a negative number, minus that number. That means that minus alpha will be a positive number. So when does alpha become negative? It becomes negative when n1 is less than n2. In other words, we've got more atoms up in level 2 than we do in level 1. Okay, so when we have more atoms in level 2 than in level 1, then negative alpha becomes positive and we get exponential gain. And then the third case is if n1 and n2 are the same, then alpha will be equal to 0, and so the material essentially becomes transparent. It stays at the same value, at rho naught. So here we have alpha positive, alpha negative, and alpha 0. So this is why I've been talking about absorption and emission in the same, as a sort of an equivalent process, because depending on what's happening inside the laser, depending on which of these conditions are true, we will have absorption. In other words, we're losing light as the light travels through the material, or we will have gain, have amplification as the light travels through the material, or we will have nothing. We'll have just transparency as the light travels through the material. Okay. Now, this has been under the assumption that we have a non-degenerate system. If we do have degeneracy, if G1 and G2 are not equal, then we have to think about the cross-sectional area, or remember the effective cross-sectional area, the cross-sectional area for the stimulated emission as being different from the effective cross-sectional area for the absorption. In other words, the absorption might have a bigger effective area than the stimulated emission, in which case you're going to get lots and lots of absorption. What does that mean? It means that there are lots and lots of different ways in which we can get into level 1 compared to the number of ways in which we can get into level 2. Okay? And vice versa, the other way around as well. So we can then look at the equations that we have. We can compare what we have found now to the results that we've already got, and we can find an expression for the Einstein B coefficient in terms of the A coefficient. The A coefficient is something we can measure. It's just a fluorescence lifetime, so it's a decay lifetime that we can measure. And all the other bits and pieces here we can measure too. And the effective cross-sectional area, the stimulated emission cross-section, stimulated emission because it's going from level 2 to level 1, is given by this expression here. So we have some constants, and then we have the line shape function. So highest gain is going to be when nu s equals nu naught. So at the peak, so when you've got your delta nu and you apply your signal at nu naught, if you apply your signal at nu naught, that's nu s, then that's where you're going to get the most effective transfer of energy between levels 1 and 2 or 2 and 1. Okay, hopefully that makes some sense. The probability of transition is greatest. And if we assume that the frequency that we're interested in is about equal to this signal frequency, which is in the center. In other words, if we think about what would be the peak value, the maximum value that we can extract from that, what would be the maximum value for G? What's G max? Well, we already looked at that. We looked at it and we found that for a Lorentzian, it was given by some number divided by delta nu, but I can't remember off the top of my head. And for a Gaussian, we had again, inversely proportional to delta nu. So these are the maximum values that we could possibly get for our stimulated emission cross-section. So again, let's look at some numbers. For Ruby was the first laser material to get to work. Its wavelength is deep in the red, nice red ruby colour, obviously. 694 nanometers, its refractive index 1.76. Fluorescent lifetime is about a millisecond or something, so 1 over, remember that tau is 1 over A. And the line width is about 3.4 times 10 to the 11 hertz when it's at room temperature. This notation of reciprocal centimeters, you'll see it maybe in some books. It's mostly chemists that use that notation, but you maybe see it. If you're interested, you can look at how do you convert from one to the other. Taking those numbers, then the effective cross-sectional area of that chromium ion inside the sapphire, remember the chromium is the impurity in the sapphire crystal that gives us the laser action. The effective cross-sectional area of each chromium ion is about 3 times 10 to the minus 20. Experimentally, you can measure it, and it's about 2.5 times 10 to the minus 20. So, a fairly good agreement there. Okay, so a small area, but remember, if you've got lots of photons, then you can hit that target.